Grounding and bonding are both essential concepts in electrical systems, but they serve different purposes. Grounding is the process of connecting the electrical system to the earth, typically through a grounding electrode system. This electrode system can include things like ground rods, ground plates, or even the metal frame of a building if it's effectively grounded. The primary purpose of grounding is to provide a lower impedance path for fault current to return to the source. This low impedance path helps to quickly trip a circuit breaker or blow a fuse, interrupting the flow of electricity and preventing electrical shock hazards. When a fault occurs, such as a live wire coming into contact with a metal enclosure, the fault current will flow through the grounding system back to the source. Because the grounding system provides a low impedance path, the fault current will be high enough to quickly activate the overcurrent protection device. Without a proper grounding system, the fault current might be limited, potentially not high enough to trip the breaker or blow the fuse. This could leave the metal enclosure energized, creating a dangerous shock hazard. Bonding, on the other hand, is the process of connecting together all the non-current carrying metal parts of an electrical system. This includes things like metal conduits, metal enclosures, metal equipment frames, and even metal water pipes. The purpose of bonding is to create an electrically continuous path throughout the entire electrical system. This ensures that all metal parts are at the same electrical potential. If a fault occurs and a live wire comes into contact with a metal part, the fault current will flow through the bonding system. Because the bonding system provides a low impedance path, the voltage on all bonded metal parts will rise to nearly the same level. This minimizes the voltage difference between different metal parts, reducing the risk of electric shock if someone comes into contact with two different metal parts at the same time. Think of it this way: grounding is like having a drain for excess electricity to flow safely into the earth, while bonding is like connecting all the metal parts together so that they are all at the same electrical potential. To further explain the difference, let's consider some examples. Firstly, imagine a metal electrical box that houses a circuit breaker. The metal box needs to be both grounded and bonded. Grounding is achieved by connecting a grounding wire from the box to the grounding electrode system, such as a ground rod. This provides a path for fault current to flow back to the source in the event of a fault. Bonding is achieved by connecting a bonding jumper from the metal box to the equipment grounding conductor, which is a wire that runs along with the circuit conductors. This ensures that the metal box is electrically connected to all other metal parts of the electrical system. Secondly, consider a metal water pipe. The water pipe needs to be bonded to the electrical system to prevent it from becoming energized in the event of a fault. This is typically achieved by connecting a bonding jumper from the water pipe to the grounding electrode system. Thirdly, take a look at a piece of electrical equipment, such as a motor. The motor needs to be both grounded and bonded. Grounding is achieved by connecting a grounding wire from the motor frame to the grounding electrode system. Bonding is achieved by connecting a bonding jumper from the motor frame to the equipment grounding conductor. Now let's delve into some specific code requirements related to grounding and bonding. The National Electrical Code, or NEC, provides detailed requirements for grounding and bonding electrical systems. Firstly, NEC Section 250.4. 8.1 requires that grounded systems be connected to earth in a manner that limits the voltage to ground on the electrical system. Secondly, NEC Section 250.4. A5 requires that grounding electrode systems to be installed in accordance with specific requirements, including the type and size of grounding electrodes, as well as the methods for connecting them to the electrical system. Thirdly, NEC Section 250.92 requires that metal enclosures containing service conductors be bonded together to create an electrically continuous path. Fourthly, NEC Section 250.96 requires that metal piping systems and exposed structural steel be bonded to the electrical system. Fifthly, NEC Section 250.102 specifies the requirements for sizing equipment grounding conductors, which are the wires used to bond metal parts together. There are different types of grounding systems, each with its own characteristics and applications. One type is the grounded system, where the neutral point of the electrical system is intentionally connected to ground. Another type is the ungrounded system, where the neutral point is not intentionally connected to ground. Grounded systems are more common in residential and commercial applications, while ungrounded systems are often used in industrial applications where a high degree of reliability is required. The choice of grounding system depends on the specific application and the desired level of safety and reliability. Bonding is equally crucial and has its own set of methods. Several methods can be used to bond metal parts together. Firstly, direct bonding involves connecting two metal parts directly together using a bonding jumper. Secondly, indirect bonding involves connecting two metal parts together through an intermediate metal part, such as a metal conduit. Thirdly, the self-bonding method utilizes listed equipment designed to establish bonding when properly installed. The method used depends on the specific application and the type of metal parts being bonded. The size of the bonding conductors is also important. NEC Section 250.102 provides requirements for sizing bonding jumpers and equipment grounding conductors. The size of the bonding conductor depends on the size of the circuit conductors and the type of equipment being bonded. It is important to use the correct size bonding conductor to ensure that it can safely carry the fault current. Grounding and bonding work together to provide a safe and reliable electrical system. Grounding provides a low impedance path for fault current to return to the source, while bonding ensures that all metal parts are at the same electrical potential. By properly grounding and bonding an electrical system, the risk of electric shock can be significantly reduced. Now, let's discuss some common misconceptions about grounding and bonding. One common misconception is that grounding is only necessary for safety. While safety is a primary concern, grounding also plays a role in the proper functioning of electrical equipment. Grounding can help to reduce electrical noise and interference, which can improve the performance of sensitive electronic equipment. Another misconception is that bonding is only necessary for metal parts. Bonding is also important for non-metal parts that could become energized in the event of a fault. For example, plastic water pipes should be bonded to the electrical system to prevent them from becoming energized if a live wire comes into contact with them. To summarize, grounding is connecting the electrical system to the earth, providing a low impedance path for fault current, and limiting voltage to ground. Bonding is connecting all non-current carrying metal parts of an electrical system together, ensuring an electrically continuous path, and minimizing voltage differences between metal parts. Remember to always consult with a qualified electrician when working on electrical systems. Electricity can be dangerous, and it is important to follow all safety precautions to avoid injury or death. Grounding electrode conductors are sized based on the size of the service entrance conductors, as specified in NEC Table 250.66. This table provides the minimum size of the grounding electrode conductor based on the size of the largest ungrounded service entrance conductor or equivalent for parallel conductors. The grounding electrode conductor is typically made of copper or aluminum and must be protected from physical damage. Equipment grounding conductors are sized based on the overcurrent protective device protecting the circuit, as specified in NEC Table 250.122. This table provides the minimum size of the equipment grounding conductor based on the rating of the overcurrent device. The equipment grounding conductor is typically made of copper or aluminum and must be run with the circuit conductors. Bonding jumpers are used to connect different metal parts of the electrical system together to ensure electrical continuity. Bonding jumpers are sized based on the size of the equipment grounding conductor, as specified in NEC Section 250.102. The bonding jumper must be large enough to carry the fault current. The grounding electrode system typically consists of one or more grounding electrodes that are connected together to form a low impedance path to earth. Common types of grounding electrodes include ground rods, ground plates, and metal water pipes. The NEC specifies the requirements for the installation of grounding electrodes in Section 250.52. Ground rods must be at least 8 feet long and driven into the ground to a depth of at least 8 feet. Ground plates must have a surface area of at least 2 square feet and be buried below the permanent moisture level. Metal water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. The connection to the grounding electrode must be made with a listed connector or clamp. When dealing with sensitive electronic equipment, it is important to provide a clean ground to minimize electrical noise and interference. A clean ground is a separate grounding system that is isolated from the normal building grounding system. The clean ground is typically connected to a dedicated grounding electrode and is used to ground sensitive electronic equipment such as computers and audio equipment. Isolated ground receptacles are often used to provide a clean ground for electronic equipment. These receptacles have a separate grounding conductor that is isolated from the receptacle's metal mounting strap. This helps to prevent electrical noise from being coupled into the grounding system. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electric shock. GFCIs work by monitoring the current flowing through the circuit and detecting any imbalance between the hot and neutral conductors. If an imbalance is detected, the GFCI will quickly trip the circuit, interrupting the flow of electricity. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, or SIs, are devices that are designed to protect against electrical fires. SIs work by detecting arc faults, which are dangerous electrical arcs that can occur when wires become loose or damaged. If an arc fault is detected, the SI will quickly trip the circuit, interrupting the flow of electricity. SIs are required in many locations, such as bedrooms and living rooms. Surge protective devices, or SPDs, are devices that are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, power outages, or other electrical disturbances. SPD work by diverting the surge current to ground, protecting the equipment from damage. SPD are available in different types, including whole house surge protectors and point-of-view surge protectors. Whole house surge protectors are installed at the main electrical panel and protect all of the equipment in a house. Point-of-view surge protectors are plugged into individual outlets and protect the equipment plugged into that outlet. The electrical codes and standards, such as the NEC, provide detailed requirements for grounding and bonding electrical systems. It is important to follow these requirements to ensure a safe and reliable electrical system. Grounding and bonding are not only important for safety, but also for the proper functioning of electrical equipment. Proper grounding and bonding can help to reduce electrical noise and interference, improve the performance of sensitive electronic equipment, and prevent electrical fires. Regularly inspect the grounding and bonding system to ensure that it is in good condition and that all connections are tight and secure. Over time, connections can become loose or corroded, which can compromise the effectiveness of the grounding and bonding system. If you are not comfortable working on electrical systems, it is important to hire a qualified electrician to perform the work. Electricity can be dangerous, and it is important to follow all safety precautions to avoid injury or death.